Dear students, in this online tutorial I'm going to talk to you a little bit in preparation for the lecture on OLS, nonlinear least squares, and maximum likelihood estimation, just to prepare you for the class. So I'm going to start here with talking a little bit about OLS, then nonlinear regression, and then variance estimation. So, as you recall, this is what the data generating process looks like for OLS. We have our xi beta, where xi here is a column vector and beta is a row vector, and plus an error term that's iid, where we have this orthogonality assumption. So in the lectures we're going to be looking at some code. So I want to show you how this works in Matlab. Okay, here's some of the code that I'm going to be giving you. Let's start with looking at the OLS code. Okay, and to make things a little bit clearer, let's start with folding the code. So if you click on fold all, then it collapses, makes the thing a lot easier to see. Alright, so we can now expand part of it at a time. So as I talked about in another tutorial, classes can have properties and methods, and we're basically only going to be using methods and static methods at that. So a class for us is basically just a neat way to collect a bunch of functions in the same file. And here are the functions that go into the OLS model. There's a predict function, simulate dataset, starting values, criterion, and estimate. So let's start with predict. What it does is it first packs out the parameters. So it says beta, that's the first, all of the parameters except for the last one, which is sigma, which we don't use here for the prediction. And the prediction of y is just x times beta. In other words, in the model, this is the prediction of y, xi beta. And this is what it looks like in code, x times beta. So if x is a column and and beta is a row vector, then this turns out as a number. And when x is n times k, this becomes n by 1, which is what we want. Okay, second, this is a data generating process, basically, or a model. What that means is it's a cookbook recipe for how to generate data. It says that if you draw some views and you draw some x's, this is how you create your y's. So that's what this function simulate dataset does. Packs out the parameters. First it sees that there are k is number of elements in theta minus 1, and those first k ones are the betas. And the last element is sigma. Then it simulates some x's. As you can see, there's a constant here, and then there's some random normally distributed variables. Oh, there should be k of those. So they're k minus 1. That's right. Because then there are k x's in total. There's a constant, and then k minus 1 regresses. And as you can see, n is an input. Then it creates x beta using this function up here, and here's how you call it. OLS, that's the name of this class. So OLS.predict takes the OLS class and the function in that class called predict, and calls it on the x that we just created, and giving it the thetas, the parameters. That gives us the prediction of y, and then we add a random normal error, rand n gives us that. Here's what it looks like, rand n of 10, 1 gives us 10 random normals, and it adds it to x beta, and then you have the y. Okay, so in other words, we can simulate a data set of y and x by hitting OLS.simulate dataset of, let's take 1,000, and let's set the parameters to be a constant of 1, beta 1 should be 2, and sigma to 3. Why not? And it's created them, and we can look at them. This is the y's, and here are the x's, and you can see the constant and the random normal error term. And if we press plot x, let's take the second entry, so this one here, against y, we want to scatter plot, it looks like this. So there's a positive correlation. Very good. Okay. Then, as you may recall, the reason why we call it OLS, ordinary least squares, is that the criterion function for OLS is that it minimizes, it's the beta that minimizes the distance, the y minus x beta squared, so the residual squared. And then it turned out, and we're going to talk about that in the lecture, that there's a closed form solution for the estimator, namely this x prime x inverse x prime y. And we can estimate the variance matrix using these equations, and you've all done that in the exercise classes and in previous subjects. So I'm not going to cover that in detail, I'm just going to show you how it works. If we go into and unfold the estimate function here, then it does that. Beta hat is x prime x inverse x prime y, using this symbol here for the inversion. And then there's a small detail on that. You can read that out here if you want to. We estimate sigma using the same formula here, as you can see from the slide here, u prime u. And then covariance matrix is estimated like this, sigma hat, sigma 2 hat times inverse x prime x. It's the same as here. And standard errors are the square root of the diagonal elements of the covariance matrix. So that's the estimate function. So if we estimate back parameters based on what we just calculated here, I press ols.estimate y comma x, then it returns these numbers as the betas, and as you can recall, we used 1, 2, 3, so it's pretty close. Alright. Finally, starting values is something we're going to be using a lot for the other classes, but not so much for the OLS class. So basically here we just return zeros, but we don't really need starting values if we use this estimate function. And criterion is, as I said before, it's y minus y hat squared. It's this thing here, but again, we estimate OLS using closed form, so we don't need it, but we're going to be needing that once we move to the nonlinear least squares, which I'll do in the next video.